Uh, you you
Yes.
you can
Then,
mention.
okay, thank you. In this part, I will present part of the work that we did with Lilia. And here we have to introduce what's the affine unimodular light-like geometry. It is a rigidification, so it's a rigid version of the full affine geometry. It can be seen as the maximal geometry that preserves the parallel vector field and the remaining metric with kernel equal to V. So how to write this in matrix form? This group is called LUN. N is the dimension. So you have the n, in fact, is not quite the dimension, but it's the dimension is n plus 1. So this is just a notation, LUN. It acts on Rn plus 1. You put one matrix, you put one, and you put a vector here, and you put a matrix in the orthogonal group. And this is the linear part, and then you you take all the translations. And this is called the unimodular lightlike affine lightlike group of dimension n. And one can see that in fact we have this isomorphism. And what I was saying before, Kahn-Walach space is Lorentzian one. Plane waves, PP waves, these are all Lorentzian manifolds. When you see the foliation, all these spaces come with a null vector field. They come with a null vector field. When you see the foliation, the codimension foliation, which is defined by V orthogonal, which is tangent to V orthogonal, I don't want to get into details, but these spaces have foliation, which is orthogonal to which is tangent to V orthogonal. V is a light-like vector field, parallel. We can prove that, or we can see by definition almost that it has this type of structure. So it is LUN Rn plus 1 foliated geometry. This is the point. Now we have this theorem that says that if you take a foliated manifold, coupled foliated manifold with light-like unimodular foliated on the so if you take a compact manifold which such that it is LUN Rn plus 1 foliated, then each leaf of the foliation is LUN Rn plus 1 complete. When you take the development map of each leaf, it will be everything, will be Rn plus 1. And this implies that the leaves are geodesically complete, in fact, because the affine space, the affine plane, has a connection, which is invariant by all the affine group. So you can pull back the connection on the leaves. So the leaves will be geodesically complete, and it coincides with the induced connection because the leaves are flat. This is part of the definition of the spaces. If you take what I was saying about PP waves. If you take PP wave, you know that it's we say that it's LUN foliated manifold. The leaves are complete, but in which sense they are complete geodesically because the connection on the leaf is the flat affine connection. It's the flat affine connection. And we proved here that they are GX complete. But the GX completeness and the connection, the affine connection, the completion with respect to the affine connection are equivalent because the affine connection is invariant under the group. This is a fact we said before. So basically, the leaves of PP wave are complete. So what we can say about the leaves, they are either cylinders, tors, or planes. You have classification. So first, when we take a codimensional foliation of PP wave, the leaves could be anything. I mean, they have affine structure, of course, but I don't know what type of these manifolds are. They are not complete a priori, but when they are complete, I can classify the leaves. These are the leaves. One thing. Second thing, we can also prove that such structures are in fact GX complete. These structures are somehow generalization of PP waves or plane waves. Let's say they are generalization of plane wave and PP wave are just Lorentzian manifold with a nice foliated geometry. This is you can take it this as definition. Flat foliated geometry. So now we relax. So this was the LU geometry. We proved completeness of the leaves. Now we relax. The question, natural question, is to relax the geometry, to take lambda here. Don't take one. Take lambda positive number. So what you have a parallel direction. You don't have parallel vector field. You have only parallel direction. And you ask question, if I have a compact manifold foliated with such geometry, are the leaves complete or no? The same question as before. Here it's L. We remove the U. The U is for unimodular. We remove the U. And in fact, the problem of completeness is equivalent that the leaves, the leaves of because we have a line foliation. You have a parallel line, so you can define a foliation on there. Integrate this line, integrate this distribution, and this is a foliation. And the completeness of the leaves is equivalent to the completeness of the completeness of this code of the F leaves is equivalent to the completeness of the V leaves. This is one statement. And in fact, there are some examples which are not LUN complete, LN complete. So when you develop the leaves, you don't see everything. You see some part of Rn. And the example is you take a Clifton-Paul torus. This is Clifton-Paul torus times S1. Clifton-Paul torus is Lorentzian torus, which is defined by means of this metric on R2 minus 0, and then you quotient, and then you take the quotient by homotheity. For example, 2 times identity. It's well this metric. This homotheity is an isometric group of this metric. So the metric is well defined downstairs. This is a compact called Clifton-Paul, and then you do times S1. Do times S1. What you know about the Clifton-Paul torus is that it has two light-like foliations. The foliation is defined by the light cone. You have two, and both are incomplete. So the leaves of each light-like foliation is incomplete. When you take, and you have that, and you know also that the two foliations are parallel with respect to the connection of the metric, are parallel. So when you take for example, one leaf, one light-like leaf of the Clifton-Paul torus, and you multiply it with S1, because the metric is product, it will stay parallel. So in the end, what you will get, in fact, you will get a leaf with L1 R2 geometry. You will get a leaf in the product with L1 R2 geometry. But when you develop it, because the leaf of the Clifton-Paul torus is not complete, the leaf itself, the product won't be complete in the end. So the incompleteness comes from the Clifton-Paul structure and the fact that the leaves, the light-like leaves, are parallel. When you multiply it, it stays parallel, and that's it. And this is the example. So here we are done with the affine light-like, but we pass to something like dual in some sense. So we put a matrix above, put the one downstairs, and we put beta. It's now a vector. It's not transposite. It's a vector, real vector. And we ask the same question, because maybe one say, okay, you are just now playing on the matrix and you are proving stuff. But the problem is that these things, we can find a natural manifold which such geometry. So it's not just we are putting the matrix and changing the order. It's not like that. So all this structure came from nature. For example, this one, in fact, I don't have an example, or I have an example where beta is 0 for this. They exist examples. In fact, this was mentioned. It was mentioned in Carrier paper. In the end, he put such a matrix, and he said that the leaves are developed adjectively. So yes. Anyways, so the name dual. Why we say this dual star? Because it preserves parallel one form. D depends on the variable here, but it's the D of the last coefficient, last variable, dxn, let's say, xn plus 1, rather than a vector field. This is preserved one form. And it has a foliation, it's stronger somehow. This is stronger in the sense that it has a foliation, not only, so it has a big codimension non-foliation inside the leaf. Also, the leaf itself is foliated. Anyways, we showed that if you take compact LU star N manifold, so this is compact, not foliated here. Here we have to be careful. This is not foliated, this is a compact. Then M is complete in the GX structure sense. And the foliated version, also true. The foliated version also true for the dual manifold. So we proved both the foliated and the compact version. Now since we are done with the dual, we pass to the pseudo-Riemann variant. So in order to instead of putting A in ON, we put it on the orthogonal group of some quadratic form index PQ. And someone say, maybe, here you are really adding stuff. Here you are really just putting some stuff, and this is not natural. But in fact, this geometry lies in the symmetric space of higher index. This affine geometry lies, you can see it naturally in the symmetric space of higher index. So even if you are, by coincidence, putting there, but somehow it came naturally from symmetric spaces. So this is a valid question. You take count value of index 2, you look at the leaves, you see this. You see LU N1 for Pn and Q equal 1. And we want to show analogous statements. So for example, Raphael Alexander, he showed that these are, if you take compact manifold, with this structure, they are complete. His paper is not published, but personally, I think it's true. This is it. I think this is true, but it's not published. However, the foliated problem can fail in the general. So you take, for example, we show that there is a 4-dimensional compact manifold which has codimensional foliation, and the foliation support geometry of type LU11. LU11, the dimension I said it's the 1 plus 1 plus 1. It's not the 1 1, it's 3. So the foliation is the dimension 3, and the leaves are incomplete. So when you develop them, you don't see all the affine space. You see only a part of it. But the development is injective. So the structure of the leaves is Kleinian. And so one can hope, though, to show that the LU1N foliated the problem, the developing up is not bijective, but it's injective. So this will show that the leaves are developed injectively. And this will be a very interesting question, because it will deal with, it will give you a big hint on symmetric spaces, or compact symmetric spaces. You can also maybe prove completeness or something like that. So the final remark in this section is that there is no foliated carrier theorem. What we mean by this? We mean that if you take, for example, a compact, say 4-dimension compact manifold, and take codimensional foliation. So there is a foliation with 3-dimensional leaves, and I say that the leaves has a flat Lorentzian structure. Flat Lorentzian in the sense of carrier, flat Lorentzian. Are the leaves complete? So when I develop the leaves, are they complete? Because Carrier proved that if you have a compact of a flat Lorentzian, then the development is, then the structure is complete. But the foliated version, what about it? The foliated version is not true. So there are some leaves which are not complete, but they develop injectively, as I said. So it stays Kleinian somehow. The example is the same one, is the 4D1, and we say that the holonomy preserves the Lorentz symmetric. So this preserves the Lorentz symmetric, and that's it basically. Now we take the dual of this variant, LU1N, the dual of this. So what we showed that if you take a compact manifold with the dual geometry LU star K1, then development is injective. It's Kleinian. but we don't know if it's surjective or no. But if dimension 3, k equal 1, then it is. Then it is complete. But in the general question is open, and we strongly believe that it's true. So it should be true. So complete, the dual. This is like this statement can be compared to Alexander, but here we show only Kleinian and complete for dimension 3. But it seems that it's true for every dimension. We are just we didn't so we didn't prove it for the we couldn't prove it for the other dimensions. Now I'm done with the dual. So open question now. So first question is to find G exfoliated manifolds. Foliated but without and preferably without ambient structure. So we don't have a big structure, but you have a tangential structure. This is like in the PP wave case, it is the case. But for the Kahan-Wallach case, is not the case. Kahan-Wallach case are homogeneous, locally symmetric, so they are homogeneous. So what I want a geometry on the leaves, but not an ambient one. I feel that this is more. I mean, if this is the case, then it's really interesting. Yes, this is one. Second thing, are the leaves are compact LU1 foliated manifold? Are the leaves Kleinian or no? This is a question now. If you take a compact LU1 foliated manifold, when you develop the leaves, are the leaves always mapped adjectively or no? This is a question. The third question, which is really interesting, you take, for example, Heisenberg, the three dimensions. Is there a gamma invariant hyperbolic foliation? What I mean by this, is there a foliation which admit a hyperbolic structure, continuous in this sense, and it's gamma invariant. So when I pass to the quotient, it gives me a compact, manifold with the hyperbolic foliation, but so it's a nil manifold, basically. It's a nil manifold. I think this is not true, impossible. Heisenberg and Euclid. Euclid also, I think it's possible. R3 is impossible. SU3. SU3, it seems that it's not true also. So it's, but you remember that it's true for Sol. It's true for Sol. But here I don't know the answer, but I'm sure that it's not true in these cases. And the final question, maybe not the final, before the last one, does S3 admit codimension one affine foliation? This is a question, so I've asked it before. It's a basic question, but it seems that it's not easy. I don't know. Note here that there is no topological obstruction. As Ala said, the characteristic of S3 is 0. So we have codimension foliation, rep foliation, for example, codimension 1. But rep does not admit. Rep does not admit. If you assume the leaves are complete, it cannot happen. But in general, we don't know. And the last question, basically, if you can answer this one, the S3 question, I think you can do this. You can classify all three-dimensional affine R2 foliated manifolds. For this, the last question, the torus, T3 has natural one, easy one, but other ones I don't know. Maybe I'm not sure. But the world of three manifolds is big, so there are many three manifolds. Anyways, thank you. Okay, before I end, I will show you just some pictures of this affine structure I told you about. I showed you the torus one. This is we call high structure somehow. This is not a translation structure, but a parabolic one. And this is radiant structure. This is incomplete. The developing here is just half space. The developing map is developing image is half space. So this I will just explain briefly that in fact the image of the developing map is everything, is every half space. This converges. It's just a picture finite here, and this is called radiant. This is all classified by some people, Goldman, Hirsch, Fried. Anyways, another picture, deformed. This is a deformed radiant. This structure you find when you deform, because there is principle of deformation. it will be something like that. This is called hyperbolic affine structure. The word hyperbolic came from the nature of the holonomy. The nature of the holonomy. Here also hyperbolic affine structure 2. Here similarity structure. Here the holonomy is just by similarity, and this is classified by Fried, in fact. And you see that point. That point is the only point missing in the development map. So the development map is everything except that point. This is why it's like it looks like the Hopf case. So it's the Hopf case. Also, this is a Hopf. This is a classical Hopf. Yeah, and this is it. Thank you very much.